Good evening, dear friends. I am going to talk to you today about Fischer information, a very interesting, simple idea, and how it can be used to determine how effective an estimator is, specifically an unbiased estimator. So, what does an unbiased estimator do? An unbiased estimator tells you that expectation of that estimator is the real value of the parameter. Real value of the parameter from the population is not known. So we are going to today tell you that how can you calculate the variance of an unbiased estimator. Does the variance has an upper bound or a lower bound? Maybe it would be enough to think that the variance cannot be zero, of course. It would be positive, but it would be all over. Whatever theta hat you figure out, the variance would be always greater than some quantity. What is that quantity? So that is a very important information that one would have. That variance of a unbiased estimator is greater than some quantity. It will be greater than 1 by some quantity. And that quantity is called Fischer information. It captures an idea of error that the estimate would have from the actual value, theta, how much the estimator has deviated. Suppose the variance of theta hat of the estimator is exactly equal to 1 by the Fischer information, then it gives you an exact amount by which my theta hat has deviated, and how much loss of information I have about the parameter theta. So this loss of information will be encoded through this Fischer information. That is how I understand the thing. I'm not a statistician, so I could be sometimes wrong. The interpretations could be different. So those who are watching my channel, even my students who were sitting in my class, and many of them who had been not been present in many of the classes, would not know what subject I actually do. Though I love probability and statistics, they are very interesting subjects, but actually my main love is optimization and its associated subjects like linear algebra, analysis, and all those things, topology, and all those kind of things. So, but statistics, though I've studied statistics for a long time, in my college days and university days, but the idea is that statistics has a huge link even with optimization. We possibly don't realize that many cases in statistics we are really solving optimization problems. Whatever be the story, let's start on. To begin with, I'd like to thank my neighbor, Dr. Shalab, who is a statistician, and he told me, looking at my earlier lectures, that I should possibly use a sketch pen to write the slides, which would be much better. So today we are going to continue talking about parametric estimation. And today's topic would be Fischer information and Cramer-Rao inequality. This is an important topic. So now we will draw a random sample, that is what's the game that we are playing, from a population, means a PDF given. We are not going to concentrate on PMF at all. You can write down the PMF yourself, figure it out. It's much more simple. PDF is something you have to do a little bit of jugglery of things. So PDF is what we are going to concentrate. So the PDF for every fixed x is a function of theta, and we want that PDF to be twice continuously differentiable, and then we will say or assume that this PDF, if we integrate fx theta dx within some range, then as a function of, you can actually, if you differentiate that integral, you can actually differentiate it under the integral sign. So the derivative of the integral is the integral of the derivative. Now this way of finding derivatives of the integral and integrals of the derivative. This is, you might think that this is a very strange kind of funny game, or to some people it might look very obvious, but it's not so obvious. It needs a reason why it could be done. So for all those mathematical reasons are actually assumed to be true in this case, all the assumptions, all the things that are needed, so that this fact that the integral of the derivative of the integral is integral of the derivative actually works. Now, this tool is very important even in computing integrals. Richard Feynman used to say that he had used this tool, or rather he used to tell, I have used this damn tool over and over and again, and he told, and he wrote in his book, surely you're joking, Mr. Feynman, that he looked very smart by getting the integrals out by computing the integrals which others could not. So this is, and of course theta is assumed to be from an open interval, maybe from R or maybe from strictly bigger than 0, something like that. So we are covering most of the standard things like exponential, gamma, beta, normal distribution, all those things. Largely our examples are from exponential and normal. What is important is to know that this idea of an information associated with a sample was first introduced by the great statistician Ronald A. Fischer. He first said that, okay, if you take a sample from this population fx theta, say sample of size n, random sample, then for the ith observation, how do I look into the idea of an information? What information does the ith observation contain in respect to the parameter theta? So here again the log likelihood function actually enters the picture very subtly. You will see what he says, that okay, take the log of the fxi theta, that is xi has the same distribution as fx. So you take the distribution of fx, that PDF, and take its log. Basically you are trying to look at log likelihood functions. Then and see how the theta changes. At x equal to xi, what is the instantaneous changes? If I fix x equal to xi, how the theta changes. So basically, and the Fischer score is defined in this fashion. Capital F of xi theta, which is the symbol for Fischer score, is the first partial derivative with respect to theta of the natural log, which is written as ln. Last time I wrote log e to tell you that I am actually using natural log, but mathematicians always prefer to write log a log e to the base e as log natural ln of fxi xi theta. So that's exactly what one wants, right? Obviously here I should have written capital xi basically, it doesn't matter. Okay, so if you now do the calculation, this is what you will have. So you take the derivative with respect to this, and then take the derivative of this part with respect to theta. This you can understand. You just apply the chain rule. Okay, done. Very good. So now there is an interesting thing. The Fischer score says the expected Fischer score is 0. That is, the observation should be such that the expected rate of change with respect to theta of the function of the density values would be 0. So even if you change theta, the density values at that point x1, x2, xn would be same. So that is the kind of, those are the densities where it is kind of x1, x2, xn, these observations are most likely. That's the idea. So I am doing this little, again showing you this computation. Expectation of f of xi theta turns out to be 0. How? Because here, if for example you write, this is the part which is this is the f of xi theta, and this is the pdf into dx over the range, which could be minus infinity plus infinity. So this again, this fxi theta and this fxi theta cancels, and it becomes del theta of this. Now this del theta can be actually taken out. This del theta can actually be taken out, right? Now this del theta, because you can derivative of the integral is integral of the derivative, so you can take this del theta out and write del theta integral of fxi dx, which is 1, total probabilities. So del theta 1, which is 0. So the total Fisher score function is you add the Fisher score functions for all the observations. Actually they would be same, because all the xi's has the same distribution. So you are taking the same operation. So Fisher score function would be same. Basically you n times sum the same thing. Though I have not written it, that is what it means. The Fisher score function. Below it you have seen already the writing called Fisher information. Fisher information is of the ith observation is the variance of the Fisher score, which tells you that, okay, I somehow try to capture a kind of error. So what the Fisher score does is that it is looking at the rate of change of the log likelihood function, and that rate of change is being captured as a function. So, and you know that the average rate of change is 0. But then how much is that error? How much change has occurred in you when you do actual observations? That is captured through this notion of Fisher information for the ith observation. I theta is the variance of this, which of course you can write it down in a much more simple way, which you need not be much worried about, because you know that the variance of any random variable x is expectation of x square minus expectation of x whole square. Now in this case, the random variable is f of xi theta. See, all these are all random variables. I am sure that you can understand from the writing that this Fisher score or Fisher information, Fisher information is a number, so Fisher score is a random variable, right? So if you now try to calculate the Fisher score, what would happen? Fisher information, it is exactly this. Because the expectation of the Fisher score is 0, it will be expectation of fxi theta whole square minus expectation of fxi theta whole square. And expectation of fxi theta whole square, but expectation of fxi theta is 0. So you just get this. So to get the Fisher information about the whole sample, you just add it n times, n I theta. For some I theta would be same. Okay. So let us now try to find an example. Let us give an example, and on that example let us try to find how to compute it. Okay. In our case, let us start with a nice one, exponential. I somehow like the exponential distribution. You must see the bias in my talks about exponential distribution. It's a very powerful distribution, by the way. A lot of things in computer science and reliability theory, exponential distribution, gamma distributions do play a major role. So they are very important in practice. It's not that these distributions are just lying on the side or kind of sidekicks to normal. Most people might think that they are sidekicks to normal, but it's not always the case. Because even distributions which are used for small samples, n less than 30. So please understand that the samples, there are many situations where large samples cannot be tested. The small samples has to be tested, and then those things become very important. So here is my exponential distribution, quite a favorite one. And if I calculate the Fisher score for the ith observation, this is what I get. You see, this is a random variable Obviously, it depends on xi and also depends on theta. Okay. Theta is of course a thing which is unknown, which is not known, and that is what you are trying to know. In statistics, we don't want to know the unknown, we want to guess the unknown. That's the difference between statistical thinking and mathematical thinking. Possibly, in a very crude way, you want to guess the unknown in statistics. In mathematics, you want to compute the unknown, you want to know exactly what the unknown is. Equation solving. So there is a little bit of difference. So here is it again. It is there in the notes. The detailed calculations are in the notes. So, but still you can have a look at it. There is no hurry. Okay. So if this goes, let me now start computing the Fischer score, ith score. Sorry, I missed the I writing. I theta. I theta is for the ith observation. What is the Fischer information? So here, you know, it is expectation of this, and then you write just what is the meaning of expectation. So now if you separate it out, this whole thing, if you calculate, you will get something like this. You can write it as sum of three integrals. So you will get this, because this integral is 1. This part is nothing but expectation of xi. And this part is expectation of xi square, which can be written as variance of xi and variance of EA plus EXI square. And these are known. If theta is the parameter of the exponential distribution, then expectation of x is 1 by theta and variance of x is 1 by theta square. So here, so expectation of x I am writing 1 by theta, and here variance of xi I am writing 1 by theta square, and expectation of xi is 1 by theta whole square, which is 1 by theta square. So this 2 by theta square and 2 by theta square cancels, and you get 1 by theta square. Sorry, there is a small mistake which I am going to correct. Give me a second. This cannot be a mistake, right? So it's 1 by theta square. Please have a look at the calculations. Please understand that expectation of xi square is variance of xi plus expectation of xi whole square, because variance of xi is expectation of xi square minus expectation of xi whole square. So you take the expectation of xi whole square to the other side and write an expression for expectation of xi square once you know the variance. Okay, fine. Right, this is done. Now we come to the Cramer-Rao inequality. How does this Fischer information gives us? So if you look at, if you want to find that Fischer information of the whole sample, it will be n into 1 by theta square. So for the Fischer information says, okay, you take an estimator of theta 1, theta 2, of theta. Let us just take one parameter. So you make an estimate. You take a random sample x1, x2, xn, and you make an estimate, right? Once you make that estimate, you do not know whether it is unbiased, biased. For example, for this kind of theta hat becomes 1 by x bar for exponential distribution. So you cannot say it's an unbiased thing. So it may or may not be unbiased. You don't have to bother. It's just, you take just an estimator, and then you calculate the bias. Bias is nothing but the difference between the estimator, the real value of parameter theta. Well, actually, it is the difference between the expected value of the statistic theta hat minus the actual value of theta. Now you can say that theta is not known. How do you know bias? So bias is usually used for an algebraic calculation. So this Cramer-Rao inequality, which can be written in terms of a bias, is really useful when you talk about unbiased operators, because unbiased estimators, because then you don't have to bother about b and theta, the bias. It is 0. And then all the information you have from the data, from the random sample. See, a bias cannot be computed from the random sample. It doesn't matter. Expectation of theta hat you will compute because theta hat is computed from the random sample. So, because these are all taken from the same distribution, you can compute expectation of theta hat. But you cannot compute, you don't know theta, so how do you know the bias? So, bias is a kind of theta dependent quantity. You can expect bias to have nice properties. For example, in bias, you can, just if you define the sample variance as 1 by n summation xi minus x bar whole square, then you can obviously define a bias. We had shown that in the class when we were in the non-corona age. So we were showing that this is how you can compute the bias. Now bias is usually